Good evening, everyone. So today we will be discussing gravity separation process, the leftover process, which was we will mostly discuss thickener design part today. And before starting today's class, maybe I will wait few minutes more to join people for the class. Okay, so we can start now. Uh, in today's class, we will discuss thickener design part. We know that thickener is one of the most widely used equipment for the liquid solid separation in various water purifications processes or plants. So we will discuss the design part of it. So before starting, we will first highlight some fundamentals of continuous thickener design. So we can know that thickener, how does it work? It works like this kind of design is having a thickener, and then there will be feed. A central well is there where there will be feed slurry, and the slurry comes out and it goes up. So there is some rising velocity towards up, and there will be settlement of solid at the bottom, and there is one more mixing kind of rake is there. It will mix, not shaft kind of, it is like a this kind of ring is there. So it will just rotate and it will scrap down. So ultimately the solid will be separated from bottom, and the liquid will come up. Clarified, the clear liquid is taken out from the as overflow. So this is what continuous thickener design thickener with that means. So we will not have. Yes. Okay. So when we talk about that kind of design thickener that we discussed, design of such continuous thickener, it requires a specification of certain cross-sectional area and the depth. So the design of that kind of continuous thickener is governed by the settling characteristics of the slurry particles or the solids in the slurry. Now the design procedure follows the Coe and Clevenger, their work or their principle. So their assumptions of the design of such continuous thickener, it includes that the rate of descent of the solid liquid interface, that means the rate of dropping down the solid liquid interface, is a function of the local solid concentration. And it is to note that it is very important that the local solid concentration in the continuous thickener process for operation, it is very important, because based upon that we will design the we will design the cross sectional area as well as depth of the thickener. So in the last class we have discussed about the batch sedimentation process. So batch sedimentation process, where we took some of the vials, suppose, and we this vial is like completely fed up, completely uh, filled with the slurry. This is the condition A. Condition B, the clarified water is there. So after the process, the settlement of the solids can be clearly visible, which is completely settled down in the settling zone, and it is known as D. So if you refer the last class uh, lecture note, you will know that we have discussed and we have learned about the sedimentation study, which is a part of gravitational separation method. So in that sedimentation study, it shows that the settling velocity of the solid, it decreases with the increasing concentration. So if the concentration in a certain layer of this kind of zone, if the increasing concentration is very high, then the settling velocity will be lesser. This is quite obvious because of the adherence of so many particles in a confined space. So it is difficult to maintain the settling velocity, so it will decrease down. But the decrease in settling velocity is less rapid comparatively. So when we are talking about a continuous thickener, there the rate at which solids settle through every zone must be at least fast enough to accommodate solids being delivered to that zone or to that depth. So in a continuous thickener operation, solids pass through the layer of concentrations between the feed concentration at the final underflow concentration. So there are a lot of layers of concentration. So if any solid entering any layer do not pass through at a rate equal to that the rate that is the solid is arriving to that layer, it will lead to increase in thickness, and the thickness layer will increase and grow upward towards the thickener overflow, and ultimately the solids will also contaminate and it will appear the overflow clarified liquid. Mostly that is water. So it is very important to balance that rate of settling, because it will lead to increase the otherwise it will lead to increase the thickness of that concentration layer, and the layer will goes up and it will goes to the point of overflow. So the solids will also present in the overflow, so clarified liquid we will not get the quality of liquid. And the last thing, that the design of a thickener is based on the rate limiting layer. So we will now uh, discuss about what is the rate limiting layer and how the concentration of that layer is calculated. So the rate limiting layer is known as which is having very lowest capacity for passage of the solids through the layer under a continuous operating condition. So now we will discuss about the concentration at the boundary of rate limiting layer. So just now we have discussed that what is rate limiting layer, that is where the capacity of solid being passed through is very lowest capacity. Yes. So here we first suppose this is one concentration layer in that sedimentation study. So this is having a certain concentration. Suppose the certain concentration here we are assuming to be concentration C of this layer, and this layer is having a rising velocity upward towards the direction of the overflow, that is VL. So the velocity at which it will this layer from the solid it will pass through, this velocity will be V plus VL, and the solids entering into the this layer will be having a velocity d plus dv plus vl. So if the concentration of the layer is C, the concentration of the solid that is entering into the layer will be C minus dc. So here VL is the rising velocity of the concentration layer, V plus dV plus VL. This one is the velocity of solids into the layer that we are talking about with respect to the layer velocity. So in this, for this kind of layer, we want to do the material balance. So what will be the material balance? You have to, and for this, the surface area which is normal to the flow, that is this one, S is the surface area normal to the flow. Now you do the material balance and let me know that what will be the material balance. You know, concentration, that is suppose gram per centimeter cube or meter cube, whatever it is. So you need to have surface area and you also need to have velocity. So it becomes grams per second, and to remove the second you need to have time. So this should be your unit for material balance. So you just write down the equations considering this layer to be used. So here you can use theta. Theta equals to that time we are considering, time for the solid to enter and then leaving that concentration layer. What will be the material balance? So this material balance, it tells that C minus dc, which is entering into surface area, into time, and the velocity dv vl. What would be the right side? That is leaving the layer. You solve the equation and you find out what will be the expression for vl bar, that is the rising velocity of that layer. So this, after doing the this will cut down, right? This will be eliminated and we will get this equation. So this will be eliminated and we will have some simplified form. This will be the simplified form. Now in this equation you will know that the term dv is there. This change in velocity is approximately 0. We are assuming. So this we are assuming to be 0. So ultimately we are having this expression as minus v. So in that expression that we got, we already know that velocity in any layer, that velocity is a function of concentration, right? So that means v is a function of concentration. dv by dc will be also the function of concentration. So for this particular layer, in this layer, concentration C is constant. So Fc and F bar C will also be constant. So if that equation, the last equation that we discussed, in this equation VL bar will be C F dash C minus Fc. So these all are constant. So VL is also constant. So from here we can conclude that VL is constant. And now go to a very specific layer which is known as limiting layer. So we have now discovered that rising velocity of the concentration layer that we are talking about, that is constant. Let's now we are uh, assuming the case. Suppose this is your sediment. This is your sedimentation study. So when initially it was fed by the slurry, it was having the concentration initial concentration C0 and Z0 is the height. This is the height. This is the case 1. In the case 2, when it got settled down, then there is interface, there is this kind of concentration layer, and the layer height is ZL, concentration is CL, and the velocity of settling of solids from this layer, that is VL plus VL bar, where VL bar is the rising velocity. Also, theta L is the time for indicates the time for solids to reach to the interface. So this is what the condition is for sedimentation study. So what will be the total weight of the solid in the slurry? That we want to know. That we know that initial concentration of C naught, initial height was Z naught, and surface area perpendicular to the flow of flux, that is S. Now we want to focus on this boundary. We want to know that the quantity of the solid which is passing through that layer, what will be the equation? That will be CL S ZL. Uh, okay. Theta L equals to, so actually these two will equal because the solids that are entering into the concentration layer, that will be equal to the solids which are passing through that layer. In equals to out, and that solids which are coming to that layer will be the total solid content of the slurry. So if you just make it equal, this equation and this equation, you will get now we already have confirmed that VL bar is constant in that concentration layer. So that VL bar will be ZL by theta L. So from this equation 2, from this equation 2, you will have CL equals to C naught Z naught VL plus BL bar. Now from this equation, you will get theta L. So we will have a plot between Z and theta. So from their plot, the slope of the plot, that will be VL. Any kind of Zi minus ZL, theta L, it will be VL, slope of the graph. But it is theta equals to theta L, that slope is VL. So from here we can have Zi equals to ZL plus theta L VL. We have to put these equations over to this equation. Now we are heading towards this equation. We will substitute here ZL and we will get an correlation. So here the correlation that we are talking about, that CL equals to C naught Z naught. So this is a very important output, that here Cl is the minimum concentration at which the boundary layers interfere, and there the settling velocity is always a function of the concentration. So now it comes like we want to when we want to design it, we got that the velocity, that how the velocity, rising velocity is connected to the concentration, and that concentration particular layer. Now we have to focus on the thickener area, which is very important because a sufficient thickener area must be provided in a continuous thickener to ensure that the specified solid's flux does not exceed the capacity of the rate limiting area. So, for any kind of thickener area, you will get that total flux equals to, so this total flux is denoted as if B plus if U, if equals to CV C into LU by A. So here C is the layer concentration, V is the velocity settling of solids at concentration C, LU is the underflow volumetric flow rate, and A is the cross-sectional area, which is perpendicular to the mass flux. If there is any question, then we can discuss in between. These are very basic knowledge and the derivation that we are going through. Now we will learn about this graph, that is the solid flux and solid concentration graph, that how we can utilize this graph for calculating the area. So when these solid flux that we have discussed in the last slide, that there is batch flux and there is underflow flux. So this equation, so this first part, it and the part 2, this gives underflow solid flux. So here in this graph you can see that at a concentration of Cl, you will have the maximum limiting solid flux at Fl, and within the range of C0 to Cu, all other concentration will give you minimum solid flux. So here, based upon this graph, we understood that Fl is the limiting solid flux capacity. So we need to provide sufficient area so that any solid flux does not cross the maximum capacity Fl. So what by this equation we want to calculate the minimum area which needs to be provided for continuous steady state operation, that will be L naught C naught by FL, this flask. In the next part, we are going to discuss about the time and concentration at the critical flask condition. Here you can see we have plotted the height of the interface, that is Z, and the time theta. At theta equals to theta c, when the height is ZC, the corresponding concentration will be Cc. And when it is Z1, that will be corresponding time of interface solids to pass through the interface will be theta u. So at this condition, what is the total mass of the solid? Initial concentration area into initial height of the interface. So from this figure we can see at theta equals to theta c, critical concentration Cc is achieved. At theta c, the settling velocity decreases very rapidly. As we all know that mass of solids is constant during sedimentation test. That means so after that you will have this equation where, for your information, this U denotes underflow. So when the sedimentation test is happening, the solids are getting settled down at the bottom. So in that displacement procedure, we are continuously displacing the water from that sliding to the upward of the thickener. So later we will uh, estimate what is the water volume to be squeezed out to reach that concentration to reach that concentration C Cu. So here what we are going to discuss that water is squeezed out to reach the concentration from Cc to Cu, right? So we need to calculate what is the water volume. This water volume, if you see the graph, you will note that water volume to be squeezed out V equals to A into ZC minus ZU. And what will be the time requirement? Theta U minus theta C. So from there we need to understand what is the volumetric flow rate. That is L equals to V by theta U minus theta C. From there V is already, we can substitute this expense like right. So from there equals to by L. So in this equation we have some unknown quantity, that is theta U, we need to calculate. For that information, at theta equals to theta C, we will get a slope, and from that we will get VC. So basically VC is obtained from the graph slope at theta equals to theta C. So what will be the value? VC equals to Z1 minus ZC by theta C. You can see this is the slope tangent we have drawn at the point theta equals to theta C, and the slope of the curve will be VC. So here the term theta C is the time when the thickening starts. And we need to calculate the theta U. So from here we can have L equals to A into VC, which is A into Z1 minus ZC divided by theta C. So in the last equation, last slide, we have also defined the volumetric flow rate L. So if you equate this to L, you will get and this L. So from there, this is the equation. Here ZU can be easily noted from this, and we have to calculate the theta u part. So at this point, we have this theta u. We can have calculation based upon the graphs, or we can easily use this equation to calculate the theta u for solids to go to the underflow section, because otherwise ultimately the solids will be collected as underflow. Now for any kind of average mass rate, that rate will be ZU A by theta u. So we derive that rate equals to theta u, and also we know so when we replace this one, so this rate can be, mass rate can be also defined like this. From there also you will get either area or either theta u. But mostly we calculate the area from here because we already have theta u from the previous expression. So we have today we have mostly discussed about the uh, thickener part, like thickener design part. So in the next class we will discuss about the other mode of separation of solid liquid, that is the centrifugal separation process. And in this class, whatever we have learned about the area for finding out the thickener, that is very important, because when you go for the separating of solid and liquid in the water treatment plant. So there, that big kind of continuous operation of thickener, that is actually operating for over period. So the rate at which the solids are collected as the underflow, and the rate at which the overflow, the clarified water is collected, those are very important for your calculations, because when you go for sedimentation process, that you clearly see the layers of A zone, B zone, and clarified zone and settled zone. So this kind of surface boundary concentration and the critical rate limiting layer, so those kind of informations are required, because the critical layer concentration is important for calculating the surface area and the thickener uh, thickener design overall. So it is very I have presented here very briefly. So based upon that, you can also calculate this kind of area calculations. So from there, if you know the initial concentration, if you know the initial um, volumetric flow rate, and if you know what is the ultimate time that the you are getting the underflow from the thickener, you will be able to calculate that what is the area required. So suppose you are not giving enough time, and you are not giving enough you are not giving enough surface area, not surface area, the cross sectional area for thickener, then what will happen, that these solids will not settle down completely at the bottom of the thickener. So it will suddenly, the layer, that with the rising velocity, the solids will not settle down completely at the bottom of the thickener, and it will go up, and it will go to the overflow. So in the overflow, we expect the clarified water but if the solids are being present in the overflow, then it will contaminate our separation process. So this is what it is happening. So area calculations is very important, and the concentration for this critical layer is also important for the calculations purpose. So if you have the data for how much the mass is entering and how much the mass is going out, so based upon that you can calculate and make the plot for solid flux versus theta, and you can have this theta u from that, and from that you can calculate the area for thickener and required area, because you already have the information of initial height of the slurry and initial volumetric flow rate of the feed. So that's it for today's class. If you have any query, then you can uh, raise question for that. In the next class we will discuss about centrifugal separation process. So, centrifugal separation process is kind of a little bit different forces that will be acting, and that is faster process and better separation, clearer separation than the gravitational sedimentation process. So we will discuss in the next class about the centrifugal process and the equipments those are being used, like um, like cone separator or centrifugal separator, basket centrifugal separator. So I guess a little bit of touch about the centrifugal basket separator we already it discussed, but we will discuss in more details regarding that equations for centrifugal force involving, and what is the better advantage of using the centrifugal separator other than gravitational sedimentation method. So you can also have that idea, like in our research purpose, that when we want to separate the liquid, like suppose we are handling with some nanofluid, so we want to separate out the nanoparticle from the nanofluid. So we need to concentrate or sediment the nanoparticles over the process. So there are two type of process. One can simply let it make the nanofluid and let it be settled for over long period, but at that point that nanoparticles will settle down and it will form a cake kind of stuff, and we can able to separate the that solvent from that nanofluid, but that takes longer time. So there is a very faster and quicker process, which is a centrifugal apparatus, which is using based upon the principle of centrifugation. So here that very easily that forms that pellets, which is very easily to be separated from the nanofluid solvent. So this is also less time consuming and also very effective process to settle down very smaller particles. So this kind of detail we will discuss in the next class. So if there is any question regarding the derivation here, that you can raise the question in the question and answer platform of NPTEL portal. I will able to answer your queries if you have any. And I will have one more lecture officially, and one extra lecture for clearing all your doubts. So whoever is not attending classes, then they can attend to clarify their doubts at the end of the session. So maybe we have uh, two more chapters to cover up, that is centrifugal sedimentation, and another one is flotation process. So flotation process is also important for a different kind of mineral processing unit. So we will discuss that also, but in the next class we will mostly focus on the centrifugal separation process. So that's it. I will end the class here today. Um, we will meet in the next session, that is next week, Saturday, usual time 7 to 9 p.m.